Inside any modern data center sits the physical engine of a new global economy. These facilities convert raw electrical power into digital intelligence at scale. Today, NVIDIA has become the primary hardware supplier for this massive industrial build-out. In fiscal year 2026, the company reported $215.9 billion in revenue, a 65% increase over the previous year. Their products include massive server racks, complex networking fabrics, and heavy physical infrastructure for AI. This dominance represents a sharp departure from the company's 1993 origins. For its first 2 decades, NVIDIA focused exclusively on the PC gaming market, building graphics hardware for home desktops. Understanding their current position requires looking at the specific type of math used to render a 3D video game. Standard computing relies on the central processing unit, or CPU. It processes data linearly, executing one instruction at a time in a fast, single stream. As data requirements grew, this serial approach hit a throughput bottleneck. Graphics processing units, or GPUs, were built for a completely different task. Their original design purpose was to calculate the color and position of millions of pixels simultaneously to maintain smooth frame rates on a screen. While a CPU handles tasks one by one, a GPU uses thousands of cores to process grids of data simultaneously. This parallel architecture perfectly matches the mathematical requirements for training neural networks. The same matrix operations rendering light and shadows now process large language models. By optimizing hardware to process massive datasets in parallel for gaming, NVIDIA provided the high-density compute environment needed for machines to learn and simulate complex reasoning. Since 2012, the computational demand for AI has grown alongside the models themselves, which have expanded from 7 billion parameters to over 70 billion. This growth forced a shift in hardware design. Processing these workloads requires more than isolated chips. It requires entirely integrated, data center-scale computing systems. This chart shows the rising energy requirements of modern servers. A standard rack uses 7 to 10 kilowatts. A dedicated AI rack demands up to 120 kilowatts. Housing this concentrated processing power creates significant challenges for power distribution and thermal management. NVIDIA's Blackwell architecture addresses these physical limits through extreme co-design. These server racks are holistically engineered, connecting 72 GPUs into a single liquid-cooled system. These AI factories function as manufacturing assets, converting massive amounts of electrical energy into digital tokens, the basic units of digital intelligence. This industrial shift resolves into a 5-layer stack: energy at the foundation, followed by chips, infrastructure, models, and applications at the top. While the hardware is the most visible layer, the ecosystem is held together by CUDA. This software platform standardizes the development environment for researchers and engineers globally. The platform maintains backward compatibility across hardware generations. Code written for older Hopper systems runs on current Blackwell hardware and will continue to run on upcoming architectures. For companies investing billions in hardware arrays, this software consistency minimizes the risk of being stranded on an outdated platform as new silicon architectures arrive. This combination of hardware performance and software stability contributed to $62.3 billion in data center revenue in a single quarter, supporting a long-term development pipeline. However, scaling this infrastructure faces physical headwinds. The intense power requirements of large-scale AI factories place considerable strain on regional electrical grids. In response, developers are using model quantization. This compresses models to lower precision formats, reducing memory and bandwidth requirements by as much as 75%. This compression makes edge AI possible. It allows organizations to run local inference on small accelerators without the need for a constant connection to a massive cloud data center. This technology is already being deployed in privacy-sensitive and remote environments, including unmanned aerial vehicles and distributed cyber-physical systems. As workloads migrate toward these low-power edge devices, the centralized data center model faces new technical and economic competition. NVIDIA is attempting to stay ahead of these shifts by accelerating its roadmap. The upcoming Rubin and Rubin Ultra architectures, scheduled for 2026 and 2027, are designed to increase compute density. These systems will use a 4x reticle design, which physically expands the surface area of the silicon to house more circuitry on each chip. The next phase involves physical artificial intelligence. This focuses on real-time inference embedded directly into autonomous robotic manufacturing and self-driving systems. This represents a transition from pre-recorded software to intelligence that is generated in real time, based on context and immediate environmental data. The global economy is shifting toward a model where intelligence is manufactured as a utility. For now, the physical infrastructure of that transition runs through NVIDIA's hardware.